So today's video is going to be 11.2, and this is actually going to be part A and then the first half of part C of 11.2 when you actually look at the Hawks homeworks. But I'm going to start with 11.2A, and right at the end I'll introduce part C. What we are doing here is formulating a hypothesis test and then conducting that test where we are conducting the test about a population mean. So if you think back to 11.1 when we were creating those null and alternative hypotheses, you saw that there were some that looked at a mean and some that looked at a proportion. Today's ones are just looking at means, so we're just going to be looking at a population mean for our null and alternative hypotheses. But the thing about our hypothesis test is that we are assuming that sigma, that population standard deviation, we are assuming that that is known, okay? 11.2b is again where we look at population means, but this time we would then show that sigma is unknown. So we're going to deal with our population standard deviation being known in this section, and then tomorrow's section is going to be where that population standard deviation is unknown. What I would recommend is if you go to the Google Drive and actually open the notes, I'm going to be going through a couple of examples that are in those notes. So it would be useful if you had those in front of you. So the first example in the notes says that an average national reading level for high school sophomores is 150 words per minute with standard deviation of 15. So we know that the national mean is 150 words per minute, and the average, or not average, but the national standard deviation, so the population standard deviation, is 15. Lincoln High School wants to see if their sophomore students read at a different level from the national average. Okay, we've got that word different in there. They're not looking at greater than or less than, they're looking at different. So this means that we're looking at a two-sided alternative hypothesis. Then the reason that they want to see if they read at a different level at this high school is because they take a random sample of 100 students at the school, and they actually found that their average reading level was 154 words per minute. So although, don't fall into this trap, although they found that their sample mean was actually greater than the population mean, if you actually read the question, what they're looking at is they want to see if the reading level is different. So even though their sample mean was higher than the expected mean, they are actually looking at, in their hypothesis, they want to just know if it's different, not greater than, okay? So we've got a sample mean and we've got a sample size, and the level of this test, remember that we talked about significance levels that would come up, that is set at 0.05. We will use that in a minute. First of all, remember that we had those steps, okay? So let's go through the steps that we would conduct in order to get a hypothesis test. So step one, we knew, was getting our null and alternative hypothesis. That's what we've looked at before. Whenever we want to test, in this case, whether the reading level is different at this high school, when we want to test that, in this case, we need to first get our null and alternative hypothesis first. We always do this. So, for step one, we're going to find H0 and HA. We want to find our null and alternative hypothesis. Now remember, the null hypothesis always states that the mean in this case, or the population proportion, but in this case we're looking at means. The null hypothesis always states that the mean stays the same, okay? That we're not changing anything from what we originally thought, it's going to stay exactly the same. So our null hypothesis is just that the population mean stays exactly where it is. You always have equality when you look at your null hypothesis. The alternative hypothesis in this case, okay, it says in the problem that they want to see if their sophomore students read at a different level than the national average, okay? So that would mean that the mean does not equal 150. That's what they want to test. Even though that they found that their mean was actually greater at that school, they just want to test whether the mean is different from what they originally thought. So that's our alternative hypothesis. When you get this, as we said, this is a two-sided alternative hypothesis. Another way of wording this is to say that it is a two-tailed alternative hypothesis. Okay, so whenever you have something that is not equal to, it is two-tailed. Okay, so it's either two-sided or two-tailed. There's a reason why I'm saying this, and you'll see it in a minute. Okay, this is all down to the normal distribution that you'll see in a minute. If you ever get something where you want to look at whether the mean is less than some value, that thing is called left-tailed. You have a left-tailed problem. If your alternative hypothesis instead is that the mean is greater than some value, whatever that might be, that is a right-tailed problem. And again, when we look at the normal distribution for this in a second, you'll see why. So you're either going to have a two-tailed, a two-sided alternative hypothesis, means you have a two-tailed problem. If you have a one-sided alternative hypothesis, it can be either left-tailed or right-tailed, depending on whether you would have a greater than or less than in that alternative hypothesis. Okay. Step 2 was to specify the significance level. So step 2 is to specify the significance level. They will always give you that in the problem. So it says in the problem, the level of the test is set at 0.05. Okay. We're going to look at what that actually means. What that means for us when we do this and when we conduct the test is that we want to end up rejecting the null hypothesis, in this case, 5% of the time. So our significance level, we always call it alpha, is 0.05. That means that we want to reject our null hypothesis 5% of the time. Okay? That means that we're 95% confident that our null hypothesis is true. We only want to be wrong about our null hypothesis 5% of the time. Okay? So, if that is the case, we've got alpha is equal to 0.05. They will always give you a significance level. Step 3 says that we need to identify the appropriate test statistic and compute its value. So we need to compute the value of the test statistic. The question is, what is the test statistic? Okay, so in this case, depending on whether your standard deviation for the population is known or unknown, your test statistic is going to be slightly different, okay? Now, if you remember back to when we did 10.2 and 10.3, particularly 10.2, if we knew our population standard deviation, we could create a Z confidence interval, okay? Our confidence interval was done using Z scores, okay? If you also remember in 10.2, when we didn't know our population standard deviation and we only knew the sample standard deviation, we had to use that student's t distribution. We were using t values. That's what happens here, okay? Your test statistic is the corresponding Z or T value. T values we'll look at in the next video. But it is going to be the corresponding Z value, the corresponding Z score for the sample mean that was given. Okay? So if you remember, when we dealt with sample means, the z-score or the z-value was given by this value. It was that z transformation, okay? We were converting the normal distribution of the sample means back to a standard normal distribution, and it gave us a z-value. That is our test statistic, okay? So this is, you can write this down so that you've got a definition. This is going to be your test statistic. Okay. It's always going to be the same with any type of problem like this. You're always going to end up doing a Z transformation, or as we'll do in 11.2b, it's going to be a T transformation, but we'll do that later on. So what we need to do here is we need to compute this value. What this tells you, if you remember what a z-value does, okay, a z-score, if you look at the standard normal distribution, which is your z distribution, you've got a mean of 0 and a standard deviation of 1, okay, in that standard normal distribution, okay? Now, if you think about it, what we started out with our sample means is some random mean of the sample means, which is the population mean, and some random standard deviation of the sample means, okay? So they're not going to have a mean of 0 and standard deviation of 1. But what this Z transformation did for us was pull it back to have a mean of 0 and a standard deviation of 1, okay? So when you actually find this Z value, okay, what it's going to tell you is how many standard deviations the sample mean is away from the population mean. It's going to tell us, it's going to give us some value of how much the sample mean differs from our population mean, okay? If it is too far away, so if our sample mean, so if we come back to our problem, okay, we've got a population mean of 150, but we found in our sample that the mean was 154. If that value is deemed to be too many standard deviations away from the mean, if our sample mean is too far away from our population mean, we would have to reject our null hypothesis, because what our sample data showed us was that it was so far away from what our population mean was, it's so far away from the value that we thought the mean was, that we can no longer accept that our mean is 150, okay? So if we do this Z transformation and we find out that our sample mean is too many standard deviations away from our population mean, we know that we will have to reject our null hypothesis. And that's what this hypothesis testing does, okay? It takes our sample data and says, okay, what does this tell us? Is it close enough to what we thought the population data would be, or is it too far away from what we thought it would be? If it's too far away, we've got to get rid of what our initial thought was, and we've got to accept that alternative, okay? So let's go ahead and compute our test statistic, okay? And that's going to tell us how many standard deviations the sample mean is away from the population mean. So let's go ahead and compute that. So we know that Z is the sample mean minus the population mean over the standard deviation over the square root of the sample size. So our sample mean is 154. Our population mean, which is the mean that we thought it would be, is 150. Standard deviation was given to be 15. And then our sample size was 100. Okay. So that's going to be 4 over 15 over 10, which is going to end up being 40 over 15. Let's do a quick calculation. So it's going to be 4 divided by, and that's going to end up being 2.667, so 2 2/3. Okay, so that is our z-score. Okay, that is our z-score for that sample mean. Okay, so it tells us how many standard deviations that the sample mean that we found was from our population mean. Now they have given us that significance level of 0.05. Okay, that's where that comes into play. So what that significance level does is it gives us a region in which we want to reject our null hypothesis. So remember I said whatever that value is that they give you, in this case alpha was 0.05, that was your significance level. That corresponds to us saying that we want to reject our null hypothesis 5% of the time. Okay? But we are going to be 95% confident in our null hypothesis. We want to say, okay, we are fine with our null hypothesis 95% of the time, and we want to be 95% confident about that. But we have got this 5% where we're going to say, okay, we're going to have to reject our null hypothesis in favor of the alternative. So that's what our significance level tells us. So whenever you get a significance level, always draw out your normal distribution curve, okay? We know that we want to reject our null hypothesis 5% of the time, 0.05. We want to accept it or fail to reject it 95% of the time, okay? In this case, as I said before, and you have to go back to the initial problem for this too, you have a two-sided alternative hypothesis. It is two-tailed. That's where the word tailed comes in. Because it is two-tailed, you have to deal with this value split into two so that you deal with rejecting the top 2.5% and the bottom 2.5%. If it was one-tailed, either left-tailed or right-tailed, you deal with that whole 5% being at the top or the bottom. But in this case, you have a two-tailed problem. So, under your normal distribution curve, you want to reject the top 2.5% and you want to reject the bottom 2.5%. So 0.025 on both ends. But you want to accept or fail to reject the middle 95%. Okay? So when you do this, what you need to do, in this case, you've got to find two values because this thing is two-tailed. So you need to find the z value here and the z value here. Any z-score that falls inside that range, so any z-score that falls between these two values, we're going to fail to reject our null hypothesis. We're going to accept what that null hypothesis says. Okay? Anything that falls outside of that range, so anything that is less than that z1 value or greater than that z2 value, means that we're going to reject that null hypothesis in favor of the alternative. So once you've found z1 and z2 in this case, you come back to what your test statistic was here, and you're going to test it. You're going to test it against these two values. If it's greater than z2, we're going to reject the null hypothesis. If it's less than z1, we're going to reject the null hypothesis. But any value, if that z value lies between z1 and z2, we're fine. We're going to accept that null hypothesis for what it is, and we're going to keep to the fact that the mean is 150. That sample mean was not far enough away from the population mean for us to worry about it, so we're still going to say that our national average was 150, okay? But if we end up with a value outside, if our z-score falls outside of the range between z1 and z2, we know that we're going to have to reject it, okay? Because 154 would just be too far away from 150 for us to stick to the fact that the mean is still 150. That means that we would therefore have to change our opinion and say, okay, well, our sample mean was far enough away from what we thought our population mean was that we need to change our thinking and we need to say that our mean is different, okay? So let's go ahead and figure out Z1 and Z2, okay? If you type this into a calculator for Z1, if you remember, we did that problem in the homeworks and the test with the grades. you had to find like the grade boundaries for a D grade or a B grade, it's very much the same as this. Okay, you're going to be doing the inverse norm. Okay, you always plug in the area to the left of the value. Okay, so in this case for Z1, the area to the left is 0.025. We're dealing with Z-scores. Mean is 0, standard deviation is 1. For Z2, you do the same thing. Z2 should end up being the negative, or actually the positive of Z1, sorry. Z1 should be negative, Z2 should be positive. But they should have the same numerical value because this thing is symmetric. Okay, so Z2 would be inverse norm of the area to the left of that is 0.975, mean is 0, standard deviation is 1. Okay, so when you do that, it ends up roughly Z1 is negative 1.96 and Z2 is 1.96. Okay, so in this case, if that is negative 1.96 and Z2 is 1.96, we now need to test our test statistic and see where this thing lies. Now the names of these Z1 and Z2 values is actually a critical value. That's what we tend to call them. And this is actually our next step in our process that we're going through here. So this is step 4, is what we've done here, is to determine the critical values or value. If you've got a one side or one tailed test, whether it be left tailed or right tailed, you're only going to have one Z value. Okay, as we'll see in a second. So you would just have one critical value. But here, because we've got a two-tailed test, we actually end up with these two different critical values. So So that's what we've done here by finding Z1 and Z2. The next thing that we need to do is to determine whether we want to reject or fail to reject our null hypothesis. So that's step 5. So do we want to reject the null hypothesis, or do we want to fail to reject the null hypothesis in favour of our alternative? Okay, so let's look back at this. So we have these critical values. And as I said, if it falls between those critical values, we're fine. We're not going to reject our null hypothesis. We're going to fail to reject it. We're going to say, okay, it's perfectly fine as it is. But if it falls outside of this, so where these blue lines are, here and here, if our test statistic falls outside of that range, then we know that our sample mean is just too far away from our population mean. We will have to reject that null hypothesis, okay? So it will fall within that 5% of the time that we will actually have to reject that null hypothesis, okay? So let's look at our test statistic. The test statistic for this problem was this Z value, which was 2.667. Well, that's greater than 1.96. So our Z value for this one actually falls around here. Okay, so this is our Z value roughly here. So because it falls within that blue range, okay, it falls within that 5% of the time that we want to reject our null hypothesis. So in this case, because the test statistic, Z, which is 2.667, falls outside of the range between Z1 and Z2. It falls in what we call the intolerance zone, actually, is the name of it. It falls in the intolerance zone. That's where we want to reject our null hypothesis. Okay, so this means in this case we're actually going to reject our null hypothesis. What does that mean? Put it back in terms of the initial problem. Okay. If we look back at our initial problem, these were our hypotheses. We're rejecting that null hypothesis in favor of the alternative. That means that we think that our mean is different than 150. So because we had that sample where the mean was 154, that gave us a test statistic. That test statistic fell outside of the range that we wanted it to fall in. Therefore, we're going to reject our null hypothesis in favor of this alternative here. So putting it back in terms of the problem, always do this at the end. So this means we'll call this step 6 if you want. So step 6, put it back in terms of the problem. Okay, this is a major step because people always forget this. They forget what they're actually trying to prove. So always put it back in terms of the problem. So in our case here, that means that we are going to accept the fact that the mean is actually different than 150. That means that we think that sophomores actually read at a level that is different to 150 words per minute. So this means, and this is nationally, not just at this high school, okay? We use the high school as an example, as a sample of all people, okay? So it's just a sample of all the sophomores in the country. But because of that being such a difference, we're actually going to say that sophomores nationally, we're looking at our population mean now, sophomores nationally have a reading level that is different than 150 words per minute. Okay. Now, it's tempting to say, as I said, that it's greater than 150 words per minute, but that is not what we were proving, okay? If you look back as to where our alternative hypothesis and what that was stating, okay, that said that it was different than 150 words per minute, not greater than, okay? So really read the question, because even though your sample might suggest one thing, that's not necessarily what we are proving. So please read the question, okay? Okay, if you look again at the notes, there is another example here that I go through. And this time we have a microprocessor designer has developed a new process that he believes will increase the life of the chip. Currently, the usable life is 16,000 hours with a standard deviation of 2,500 hours. A random sample of 1,000 microprocessors was tested and they had a mean life of 16,200 hours. Test the hypothesis at the 0.01 level. Okay, so for a start, he believes that it will increase the life, okay? So because he wants to test whether there is an increase in the life of the chip, we know that we are looking at a greater than scenario for our alternative hypothesis. So again, let's go with step 1. We're going to find our null and alternative hypothesis. Okay, we want to see what we're actually testing. So our null hypothesis, okay, states that the current mean life is 16,000 hours, okay? But the alternative hypothesis, he believes that with what he's done here, he believes that the mean is now greater than that. That's what he wants to test. He wants to test whether there is an increase in the life of the chip. So we are testing that. So we now have a right-tailed test. Okay, because we have a greater than, it is a right-tailed test. If it was a less than, it would be a left-tailed test. Okay, next step, specify the significance level. So specify the significance level alpha. That's the level that we are testing at. So in this case, we want to reject our null hypothesis 1% of the time. Okay. So it says in the problem that we want to test this at a 0.01 level. So we want to end up rejecting our null hypothesis only at the top 1%. Okay. Next, it says to identify the appropriate test statistic and to compute its value. So step 3 is to find the test statistic. Okay, again, that's that z value. We are given the population standard deviation, so we know that it's a z value. So your test statistic is the sample mean minus the population mean over the standard deviation divided by the square root of the sample size. So I'm going to have to do this on the next page. That equals the sample mean was 16,200. Population mean was 16,000. Divided by, now the standard deviation was 2,500. And our sample size was 1,000. So square root of 1,000. Okay. If you compute that on a calculator, you get 2.53. So that is your z value. Okay, that is your test statistic. That's what we're going to use to compare to the critical value to see whether we're going to reject or fail to reject our null hypothesis. Okay, so that means, if we look at this, that means that our sample mean was 2.53 standard deviations above what the population mean was. Okay, remember, a standard deviation of the sample means is the standard deviation over the square root of the sample size. Okay, so what this value tells us is that our sample mean here was 2.53 times this value away from this. Okay, and it was above it. Okay, now the next thing is to determine the critical value. Okay, so to determine the critical value, okay, we go back to what our significance level was and what our alternative hypothesis was. So we said that our significance level was 0.01 and we had a right-tailed test. So when we look for our critical value, we want to reject the top 1%, okay? It's a right-tailed test. Your tail is going to be on the right, okay? The tail where you reject is on the right, okay? Because we've got a greater than, it's going to be a right-tailed test. We reject the 1% that's on the right, which means that we want to fail to reject the null hypothesis. We're going to accept what the null hypothesis says 99% of the time. So the question is, what is this critical value? We'll call it Z1. Okay. Calculate it the exact same way as you normally would. Z1 is the inverse norm of the value to the left of it, the area to the left, mean of 0, standard deviation of 1. If you do that, your critical value ends up being 2.33. Okay. Step 5 is to determine whether we want to reject our null hypothesis or not. So that's where you have to look at whether this test statistic you found, this z value here, whether that falls in that danger zone, whether it falls in that intolerance zone or not. So you want to see, does your test statistic that you found fall in this range here where we would reject our null hypothesis, or do we accept it as it is and we fail to reject the null hypothesis and we still think that the mean is 16,000? Well, in this case, you get z is 2.53. That is above 2.33. So we know that our test statistic falls up here. So again, in this case, step 5, where we determine whether to reject or fail to reject our null hypothesis, okay. In this case, because it falls in that intolerance zone, okay, it falls in that 1% where we want to reject our null hypothesis. That means that we're going to reject H0. Okay, so we're going to reject H0. Then step 6, put it back in terms of the initial problem. So because we are rejecting our null hypothesis here, that means we are rejecting it in favor of our alternative hypothesis, which means that the mean is actually greater than 16,000, okay? So given his sample data, we can actually see that the sample mean was too far away from our initial guess of the population mean, which means that overall we think that the population mean is actually higher than what we initially thought, okay? So that means that the chips have a life of greater than 16,000 hours. Okay. So this new technique that they are using is succeeding in making those processors superior, okay? Because they're going to increase the life of the chip compared to what they initially were, okay? Now, we've gone through all of this, and this is, as always, the long way of doing it, but you need to know how to do it. The way that Hawks actually sets it up is you're supposed to learn the long way of doing this for 11.2a, and then again, when the standard deviation isn't known, we're going to learn the long way for 11.2b. But they don't actually teach you the short way until 11.2c. What I'm actually going to do is I'm going to show you the case as what we have here, where that standard deviation sigma is known, and then I'm going to show you the short way of doing it. So I'm going to cover the first part of 11.2c. Then next time I'm going to show you when sigma is unknown, and then I'm going to show you the short way of doing it. So next time I'll do 11.2b and then the other half of 11.2c. Okay, but I want you to see the short way of doing it because it may help you with your homework. You do have to do some of these steps within Hawks, okay? But the short way of doing it makes it so much simpler. So I want to tell you how to do that on your calculator. So let's go back to our original example. So it said that we've got an average national reading level for high school sophomores is 150 words per minute with a standard deviation of 15. So I know that on average for my whole population, the population mean is 150 words per minute and a standard deviation, a population standard deviation of 15. Then it says that the school wants to see if the sophomore students read at a different level from the national average. So again, we knew that that was a does not equal for the alternative hypothesis. Then it said that they've given us this level, which is 0.05, and we've got a random sample of 100 students at the school. So they've got a sample of 100, and their average, that sample mean, was 154 words per minute. So we want to conduct this test. Now we've already done it the long way. Let's do it the short way in our calculators. You have to keep in mind here that you know what the population standard deviation was. Taking you back to what we did when we did confidence intervals, remember, if you knew what the population standard deviation was, we did a z interval in order to find the interval that contained the population mean. So when we knew the population standard deviation, it was a z interval. When we didn't know the population standard deviation and only the sample standard deviation from our sample data, then it was a t interval. In this case, we have our population standard deviation. So going along those same kind of lines, remember, when you know your population standard deviation, before with confidence intervals, it was a z interval. In this case, what we're going to be running when we're running a hypothesis test is actually a z-test, okay? When we go ahead and actually do this where we know a sample standard deviation but not the population standard deviation, it's going to be a t-test. So they do match up. So it's all about whether you know the population standard deviation or just the sample standard deviation. So in this case, we know our population standard deviation. We want to conduct a hypothesis test. It's a z-test. So let's go to our calculator. And you're going to go to Stat and go across to Tests. Okay, your very first option is z-test. We're going to come to t-test in a later chapter, but right now we're conducting a z-test.
you have statistics, okay? You haven't been given a list of data, so you haven't got a list of all of their scores, okay, and how many words per minute they can read, okay? You have the actual statistics, you have the summary statistics. So we know from our problem that our population mean that they're trying to test to see whether it's actually true or not. Our population mean was 150. That is the number that goes into your hypotheses. Okay, so whatever number you have in your hypotheses that you're trying to prove or disprove, that is the number that goes in mu0. That's your population mean that you're trying to see if it is true or not. So that goes in as 150. Then we've got our population standard deviation, that was 15. Our sample mean was 154, so out of the 100 students, so n was 100, we know that they had an average score of 154 words per minute. Then we've done this before when we went through the actual steps for this problem. We know it is a does not equals because we know that they want to know if it's different than 150 words per minute. And now we're going to go ahead and calculate. And it's going to give you this information. Now, the test statistic, that z-score that we're using as our test statistic, is this top value here. The value that I really want to know right now is actually this p-value. This is the value that we are going to focus on. And we're going to compare this to our value for alpha, and that's going to tell us whether we need to reject or fail to reject our null hypothesis. So keep that p-value in mind.
The p-value on your calculator on that third line down, it is the probability of observing a value of the test statistic that is at least as extreme as the value that you got for your test statistic. Okay, so let's look at the example that we had here on this page. Okay, what we have is a test statistic of 2.53. Okay, the p-value on your calculator is the probability that you will get a test statistic that is at least as extreme, if not more extreme. So what it effectively is, whether you have a left, right, or two-tailed test, this is going to change, but it is the probability that it is at least as extreme as this value, which means in this case, it would be the area under the curve to the right of that value, because it's the probability that I would have a test statistic that is either that value or more extreme than that test statistic. So in a right-tailed test with what we have here, okay, it's the probability that I would have that value or greater. Okay, so it's the area under the curve from that value and to the right. Let's come back to our other example that we had to look at what the p-value would be here, okay? Now, I said that our z-value in this one would be roughly here, okay? What was our test statistic? It was 2.667, okay? So your test statistic in this case is 2.667. In this case, the p-value that you would get, okay, as this is a two-tailed test, would be the probability that I am at least as extreme as this value. So I'm at this value or greater, or I take the negative of it and I am less than that value, okay? So it is the probability that you are at least as far away from the mean as you currently are from the test statistic that you have, okay? So in a two-tailed test, it's the probability that you're at least as extreme as where you are or further out on both sides. Or on a one-tailed test where you're right-tailed, it's the probability that you are greater than that test statistic. And in a left-tailed test, it would be the probability that you are less than that test statistic value. Okay? So that p-value, we'll write this down. Okay? The p-value is the probability of being at least as extreme as the test statistic value. Okay. Now, because of that, okay, think about that significance level alpha, okay? We computed a critical value based on what our significance level alpha was. So we computed either a Z1 or a Z1 and a Z2 if it was a two-tailed test, okay? And that was all based on what the value of alpha was. That's how we kind of drew it out and how we figured out our values. If you look at a picture, okay, alpha in this case was the area under the curve here, okay? So it was the area under the curve where you went from Z1 and to the right, okay? It was that area under the curve. But we found that with our p-value, with that being the probability that you are greater than that test statistic, that would mean that the area under the curve to the right of the test statistic was less than the area under the curve to the right of Z1. Okay, the area under the curve here to the right of the test statistic is smaller than the area under the curve to the right of that critical value. Okay, because it was further over, okay, it was more extreme. Come back to this example here. Okay, if we look at this example, the area under the curve to both the right of the test statistic and to the left of the negative of the test statistic, because we've got a two-sided test here, so we've got to deal with both sides and being at least as extreme on both sides, okay? The area under the curve to the right of the test statistic here and to the left of the negative of the test statistic here, so we deal with being at least as extreme on both ends, that area between the two is less than the area under the curve to the right and the left of each of my critical values. Okay, so my p-value, if it's less than alpha, my significance level, because alpha is the area under the curve, in this case to both the left and the right added together. In our other case here, our alpha value was just the area to the right because we had a one-tailed test. Okay, if your p-value is less than your alpha value, that must mean that your test statistic is more extreme than the critical value. And that means that you reject the null hypothesis. Okay, so this makes it super easy. If you go through and do a z-test on the calculator and you find that your p-value is less than that significance level alpha that they give you in the problem, then you always reject the null hypothesis, regardless of whether it's a one-tailed or a two-tailed test. You tell your calculator that, it will calculate a p-value for you anyway. So it takes into account it being a one or two-tailed test, okay? But if your p-value is less than your significance level, you always reject the null hypothesis. If it's not less than alpha, if it's actually greater than alpha, that means that you're going to fail to reject, okay? Because that means that your test statistic does not fall in that intolerance zone, okay? It's going to fall within that safe region, okay? So if P is going to be greater than your significance level, when you put it on the calculator, you're going to fail to reject H0. That is a super quick way of dealing with this. And then all you have to do after you've done that is sum the problem up and state a conclusion in terms of the initial problem. Okay, but this will be a really easy way of telling you whether you reject or fail to reject that null hypothesis.